Okay, welcome back to the afternoon session of the afternoon session, and our first speaker is Professor Alok Shukla. You have already heard him in the morning. We'll be continuing that schedule again. So please, Alok sir, over to you.
Okay. Okay, so actually, I had covered all the conceptual aspects of the CI approach and had started to talk about first application. Just in case there are some people who were not here, who were not there in the morning session, the first application addresses the question which was predicted long time back, whether acenes, long acenes, in particular nonacene, does it have a triplet ground state? Okay. So we had used PPP model to perform calculations on three long acenes: octacene with 8 rings, nonacene, and decacene. Octacene and nonacene, we undertook those because a group in Germany had synthesized those and had performed measurements on them. So we wanted, and they wanted some guideline from our group as to what is the nature of the ground state. Is it singlet or triplet? Because they had not performed magnetic measurements. They had only performed optical measurements. So first thing, and then just for the sake of it, we decided to go one higher, uh, one lo- one longer, the next longer acene. That is, we decided to extend not only, we decided to perform calculations not only on octacene and nonacene, but also on decacene, just in case someone synthesizes it in the future. So all this I have covered. We performed first. What we did is that we performed simple calculations of lowest triplet state and lowest singlet state to see, and lowest triplet state is of B2U symmetry and lowest singlet state is of AG symmetry. Okay, and we just wanted to see if the triplet state was becoming lower in energy as compared to the singlet state, and if we define the spin excitation like this, energy of triplet minus singlet, then this quantity should become negative. And as you can see in our calculations as well as in many other calculations, in none of the calculations, nona seen is having a triplet ground state. Okay, so this all the theoretical calculations predict that nona seen up to nona seen and even up to decasene, the ground state should only be singlet. And there's a significant in electron correlated calculations. There's a significant uh, spin gap, okay, of 0.5 eV up to decasene. So it is not likely to close even for longer acenes. Okay. So this issue is settled. But like I said, okay. And the another thing which is interesting from the theoretical point of view is looking at the ground nature of the ground state wave function. So dominant configuration in the ground state wave function for I mean for here we are giving the ground state wave function of I believe I have forgotten to mention whether it is octacene or nonacene. Okay, let us. I think it is nonacene, but I'll have to. But it doesn't matter because we. Oh, sorry. I mean the n value is given here. Okay, so what we have done is that we have plotted. See, the dominant configuration in all the cases still is the Hartree-Fock configuration. That is all the orbitals W occupied till you fill all the orbitals. Okay, and they will always have AG character, AG point group symmetry. So that is the Hartree-Fock closed shell configuration. Now there was a claim in theory, by DMRG people and all that, and others also, that even though AG is the ground state, but it begins as the length of the oligomer increases, you start getting significant contribution from doubly excited configurations, and two types of doubly excited configurations in particular. One, both the electrons from HOMO are excited into LUMO, which is a closed shell configuration, but not the Hartree form configuration. And another one where one electron is excited from HOMO to LUMO, and another one is excited from HOMO -1 to LUMO +1. Okay, and so this is the contribution, the magnitude of the contribution of these two. CS stands for the first configuration, and OS, meaning open shell, stands for the second configuration. And here, as a function of n for both sets of parameters, that is starting from pentacene all the way up to decacene, okay, we have plotted the contribution of both closed shell configuration and open shell, both with standard and screen parameters. And with both sets of parameters, we see that there's a clear-cut trend that the contribution with the increasing length of the oligomer appears to increase. Okay, it is continuously increasing. Now, such molecules which have, singlet structure but have a significant open shell or configuration mixing are called are said to have open shell diradical character in the language of chemistry. Okay, so this simply shows that indeed long acenes have significant open shell diradical character. Okay, so I have already spoken about, I just discussed all these things, that ground state of longer acenes begins to exhibit significant configuration mixing, and with the increasing oligomer lengths, the contributions of several doubly excited configurations to the ground state wave functions increase, and longer ones, 8, 9, and 10, exhibit a tendency towards a singlet ground state with the significant diradical open shell character. Okay? So that issue is settled. Now coming back to, although our calculations indicate that singlet is lower than triplet for all the oligomers considered in this work, and probably even longer. However, that is only a calculational proof, okay, a computational proof or whatever you call it. But we need to also, it will be great if we could directly demonstrate that by either by measuring the angular momentum or the susceptibility, magnetic susceptibility, and demonstrating clearly that the ground state has a singlet character, okay, or some other means. But Bettinger et al. Had not performed any magnetic measurements; they had only performed optical measurements. So I thought, let me try this. That let us calculate the the optical absorption from the ground state, that is the singlet state, and let us also calculate the optical absorption from the triplet state using our configuration interaction methodology, and compare with the optical absorption which Bettinger et al. Got, that is their experimental results. And if there is a sufficient difference between the two optical absorptions, two absorption spectra, and if one of those agrees with the experiments, then we can settle the issue which one is the ground state. So to make a long story short, we saw a significant fingerprint of the spin level, okay, spin multiplicity in the optical absorption spectrum, okay, and our singlet absorption spectrum agreed very well with the experimental results. So here there are some technical details. Okay, so if I consider, if I calculate the optical absorption from the singlet state, then we know that the point group symmetry is Ag. Okay, so it can have, as per dipole selection rules, it can have a Y-polarized excitation into B2U type of states, okay, and X-polarized excitation into B3U type of states, okay. And here are the parameters. I told you in the morning that we took uniform bond lengths and uniform bond angles, okay. And the other complication was that they did not really, I mean, the experimenters did not have the oriented samples, because if they had oriented samples, by comparing the polarization of the in the absorption spectrum, we could directly figure out whether it is from triplet or singlet and all that. So we really we lack that information as well. So we really had to look at the entire spectrum. Okay, so here, if so, this is the scenario. If the ground state is singlet, I mean, these are the selection rules. And if the ground state is triplet, that is triplet B2U, then it will reverse, that is X, because now the reference state is B2U type. So X polarized excitation will be in B1G type of triplet states, and Y polarized excitation will be in AG type of triplet states. Okay, and this is very simple group theory, which is available in any, I mean, it's all available also on the websites. Okay, so then we just did really high quality MRSD CI calculations of the lowest AG state, as well as higher states of, I mean, when we were looking at the singlet spectrum, then we had to calculate the excited states of B2U and B3U symmetry. Okay, and because our code is symmetry adapted, so we were able to separate the two. For AG manifold, we had to calculate only the ground state. Okay, and for excited states, we could again split the Hamiltonian into B2U and B3U, thus thereby reducing the dimensions significantly. Okay, and we calculated the spectrum. And the main feature of the spectrum, so this is on the left we have octacene, and on the right we have nonacene. Okay, and standard and screen parameters. Okay, so what we have on the top, we have standard parameters, and on the bottom we have screen parameter results. Okay, so but if you look at the spectra, the main characteristic feature is that the first absorption is bipolarized. Okay, and it's weak, and then there's a very intense peak, X polarized. Okay, for octacene using both sets of parameters, and for nonacene using the standard parameters, this intense absorption splits into two X polarized peaks, but which are very close by. But using screen parameters, it is still one peak. Okay, so first weak absorption, and then at a higher energy, we have a strong absorption. Now here we cannot, if we have the oriented sample, then by looking at the polarization, we could predict what is the truth. Okay, but here we don't have oriented samples, so therefore we will have to really look at the entire spectrum irrespective of the polarization. Okay, and compare the results. Okay, so this is these are insignificant. I mean, these are technical details which one need not know. Now, when we calculated the triplet absorption spectrum, okay, that will correspond to a photo-induced absorption. That is, first you promote the system to a triplet state, which is higher. All calculations suggest, and then you consider an excitation into higher triplet states. So here, one very good thing which happened, which and we were lucky in that sense, that the spin multiplicity does leave a fingerprint in the optical absorption. Here, what we have is the spectrum, triplet absorption spectrum, exhibits two peaks. Okay, both two intense peaks, and both are X polarized. Okay, as you can see. Okay, so then because Bettinger et al. Had really done a very good optical absorption measurement, so it became easy for us. And indeed, what we found is that the true optical absorption spectrum was of this type, that they saw one, I mean, uh, or rather several smaller intensity peaks, weak peaks. Okay, we are also getting several. Okay, and then one very intense peak. But and so we looked at, when we compared the I mean, our data with the experiment, we looked at the location of the first absorption and relative intensity, and the location of the most intense absorption. Okay, and indeed, so here the entire data is given, and you can immediately conclude that the absorption, experimentally measured absorption, matches much more with the, I mean, singlet absorption as compared to triplet absorption. Okay, so therefore, this is an optical finger or optical spectroscopy confirmation of the fact that indeed the ground state is of singlet type. Okay, so for example, if you look at the numbers in octacene, the experiment saw the most intense peak at 3.78 eV. In octacene, our calculation predicted the most intense peak with standard parameter to be 3.38 and 4.17, so roughly in that ballpark region. And the first feeble peak was in the range experimentally 1.54 to 1.86. Okay, and in our case, for the triplet absorption, it is 1.49 to we got 1.49 with screen parameters and 2.24 with the standard parameters. Again, in reasonable, I mean, screen parameters results are in very good agreement, and standard parameters are in the ballpark. And you can see the same story regarding donacine. So, by combining our calculations of optical absorption from singlet and triplet states and comparing with the results of Bettinger et al., we both the groups decided to conclude that indeed the ground state is triplet, is singlet. But the most definite confirmation will be if someone could measure the, magnetic, someone could do magnetic susceptibility or ESR or some kind of measurement and show very explicitly that the angular momentum is zero or the spin is zero. That is, it's a singlet one. But all indications so far are that indeed the ground state is singlet. Okay, so this is the basic conclusion of this work. Okay, and now let me see how much time I have. I have about 40 minutes. So let me move over to, okay, next set of calculations which we have done, which I have included in these slides, are some calculations on quantum dots. I would like to come back to it, and they were also done using PPP model. So I will just explain briefly that why for graphene quantum dots we were able to use PPP model. But before that, I would like to move over to one problem involving clusters, that is B12 cluster, because I find that quite interesting. Okay. So I will give a brief introduction as to why graphene quantum dots are interesting and all. So graphene is a very interesting material, but then you can also cut it into finite fragments, particularly if you want to introduce the gap. Okay, you can cut it into finite fragments and then perform. Finite systems always will have a gap. Okay, and calculate their various properties. In our case, the properties of interest were of optical properties. So you can have a trigonal quantum dot with zigzag edges. You can have a trigonal quantum dot with armchair edges. You can have hexagonal quantum dots. This is the work. This molecule, hexagonal molecule, is coronine, and I was involved in a calculation with Sumit's group on coronine and some other hexagonal molecules. Then you can have diamond-shaped quantum dots and things of that type. Okay, now the question is, PPP model was proposed for aromatic hydrocarbons, that is planar pi conjugate systems. Now, where does graphene come into the picture? So the moment we introduce a finite fragment of graphene and don't saturate the edges, it will undergo edge reconstruction. Okay, and it will not look anything like this. It will distort. Okay, due to edge reconstruction, dangling bonds will try to saturate each other, and structure will distort like anything. So you can have these structures only if you saturate the edges with some atom like hydrogen, and the moment you saturate the edges, they become hydrocarbons. Okay, so planar hydrocarbons. And so what we have assumed is that these so-called graphene quantum dots are actually planar hydrocarbons, but of the desired shape, and many of them actually are well known. Well before graphene came into the picture, they are well known as polycyclic aromatic hydrocarbons in the organic chemistry community. So that is something I learned when we started comparing our results to the experiments. Okay, so because we are assuming that all these structures are saturated by hydrogen, so they become hydrocarbons, and therefore the PPP model can be applied. Okay, and rest of the stuff is basically that again the argument that graphene is a planar system and therefore it will have sigma pi separations. So we ignore when we apply PPP model, we ignore the sigma bonds or sigma electrons. We just include the influence of sigma electrons is included in the hopping, and only the pi electrons are the ones which matter to us. Okay, and then we can just take whatever methodology has been developed in as far as PPP model is concerned when applying it to hydrocarbons, we can again use the same thing. And this is the philosophy which I used. And here are some of the publications which came out of it. So this is the paper on coronene and other related hexagonal fragments with the experiment theory paper with Sumit's group, then pure theory paper with Sumit's group, then our own theory papers, okay, 2015, 2016, then in 2018, okay, this was on a triply bonded system, graphenic structures, okay, diamond shaped quantum dots, magnetic properties, then rectangular quantum dots in 2019, then with Preetham, who will give the last talk today, on lower symmetry polycyclic, coronene derived, but not exactly coronene molecules. And last year we looked at graphene quantum dots with Stone-Berry's defects, again with Pista and Fukushima. And this year we looked at graphene quantum dots with dye vacancies. So these are we have been fairly active in this field. Okay. So, but I would like to come back to this later because this is very similar to methodology, is very similar, and Hamiltonian is also identical to what I discussed just now, octacene, nonacene, etc. So, I would like to go to a problem related with clusters where we did not use PPP model, we used perfectly ab initio methodology. And let me see if if the time remains, then I'll come back to one of these graphene quantum dot problems. So let me go to B12. So it deals with geometry, ground state geometry, and optical absorption of B12 clusters. That is 12 boron atoms arranged in some way. Okay, but why is it of interest? Why should anyone bother about it? See, boron, being a light element and highly reactive, is not found in you cannot mine it. Okay, there are many metals you can mine, but boron is not found as boron on Earth. It is always found in one of its compound forms. So you have to purify. Okay, and then there are various. When it comes to bulk boron, there are various structures. But one thing common to all the bulk structures, bulk isomers of boron, is that the units, the fundamental unit seems to be a icosahedron, the minimal icosahedron, which should have 12 vertices, B12 icosahedron, which has IH space group, okay, point group. Okay, so IH is also the space group of Buckminster-Fullerene, but Buckminster-Fullerene has 60 atoms. Here, this is the smallest cluster which will satisfy IH symmetry. Okay, 12 atom. So the minimal icosahedron is a 12 vertex structure. So it is seen that bulk boron, pure bulk boron, is made up of these B12 structures, icosahedron. But if you try to envision a isolated icosahedron, it doesn't exist. Okay, so the question is why? In bulk it exists, but it doesn't exist in free form. Okay, it will always distort to a lower structure. Okay. So what I'm going to, the rest of the story that I'm going to tell you is based on this paper, which is with Preetham and Ihsan Bustani, who has been working on boron for a very long time. I do some calculations on boron here and there every couple of years, but he has been consistently working in this field, and he was our collaborator. So he suggested the problems, and then uh, Preetham did the calculations using MRST, and various other methodologies. Okay, so what we decided is that we decided to consider 12 atom structures, B12, chemically speaking, but we did geometry optimization in such a way that all possible stable structures, stable or unstable geometries, which we get, we will consider those. Okay, so that can be done. If anyone has experience with the molecular dynamics simulations and all that, you can do that. So the calculations were performed using Gaussian package and correlation consistent polarization variance double zeta basis set. And at that time, we used Gaussian 9. Now we have access to Gaussian 16 also. And the calculations were all done on singlet states. You can have, for a given cluster, you can have any multiplicity which is consistent with the number of electrons. Okay, but we considered the singlet states, and we found several isomers. This is not to say we found 11 isomers, which I'll show on the next page. Okay, but these are not the only. We cannot say that these are the only isomers, because you can arrange 12 atoms in many ways. Okay, so one isomer we are sure of, it's this pseudo triangular structure, the first one. So A, B, C, etc. proceed from top left to right. Okay, so this is the first one on top is A, and the last one is F. Okay, so people have done measurements, and they found that more often than not, when they do the calculations and also experiments on B12, then they find this structure, which is listed as A. It has a C3b symmetry, point group symmetry, which is a non-abelian group, but it's not a planar structure. Okay, it is quasi-planar with slight curvature. Okay, so this is for 12 atom borons, B12. This isomer is definitely the lowest energy state as per theory as well as experiments. But we decided to explore other ones because, like carbon exhibits a lot of allotropes. So similarly, boron, same is true of boron. So we found some cage-like structures. We found chain structures. Then again, planar structure here. Okay. Then this is the perfect icosahedron, which we found. It is not of the lowest energy. I'll show you the energies also. Okay, and perfect icosahedron, then a distorted icosahedron which has D2H symmetry we found. Okay, and then other cages with different point group symmetries. This is like um, triangles stacked on top of each other, and finally a planar square structure with D4H. So these are all the structures we found, but this is if we arrange their total energies in the ascending order, then we find that quasi-planar, consistent with the experiments, is the lowest in energy. Then double ring is higher. Then chain structure is higher. After that, hexagons, perfect icosahedron, and all that. So for several of these, and so if we consider quasi-planar structure to be the ground state, that is, so we measure energies with respect to that. So you can see that other structures are higher in energy by at least 1.8 eV as compared to C3b. Okay, and perfect icosahedron is significantly higher, 3.86 eV. So, but see, sometimes what happens is that you optimize a geometry, and you will get an equilibrium geometry which is an unstable equilibrium. So in order to determine whether the equilibrium geometry you obtained is a stable equilibrium geometry, or it is an unstable equilibrium, or a saddle point or something like that, then you have to calculate the vibrational frequencies. Okay, that is also done in Gaussian. Okay, so, and that is called vibrational frequency analysis. So if you get all the frequencies, vibrational frequencies, to be real, then that means the system is stable. if you get some of the frequencies or omega square to be negative and hence frequency to be imaginary, that means you are sitting on a saddle point somewhere, okay, and unstable equilibrium. So we were interested in like lower energy structures. So we did the vibrational frequency analysis on first three isomers, that is quasi-planar, double ring, and chain, okay, and they were all found to be stable. Okay, so no imaginary frequencies. Then we looked at, because the whole work was motivated by perfect icosahedron. So we found that this one has actually five, I think five or four. Okay, let me, all that data is here. So for IH structure, five imaginary frequencies were found. So that means clearly it corresponds to a saddle point. So then it will not be stable at all. Okay, it will get a jerk and immediately distort to a lower energy state, which is stable. So I mean, if we what we do is that if we take the IH structure, optimize IH structure, and again perform molecular dynamics, we get another structure which is distorted icosahedron, okay, with D2H symmetry, okay, not perfect icosahedron. So then we took this and again started a new molecular dynamic simulation. This was also this also distorts into hexagonal structure and so on and so forth. So we found that for perfect icosahedron and distorted icosahedron, both they had imaginary frequencies, so naturally they were unstable. Okay, so this is in perfect agreement with the work, now somewhat old work from 2003, published in Nature Materials, where they looked at several boron clusters, in particular boron 12, and experimentally and theoretically also they found B12 with the C3b structure to be true ground state. Okay, but we thought that let us try to understand as to why this IH structure, perfect icosahedron, which looks so symmetry, why is it unstable? So then it occurred to us that perhaps we should do some Yarn-Teller analysis, because we know from Yarn-Teller theorem that many times highly symmetric structures are unstable because of the degeneracy in the ground state. Okay, so then we decided to pursue that channel. Okay, so we performed Yarn-Teller analysis of this IH structure. So then what is Yarn-Teller theorem? So there are various terms going around for this: Yarn-Teller theorem, Yarn-Teller distortion, Yarn-Teller effect, and all that. So there are several statements of this Yarn-Teller. Okay, but basically it implies that if a non-linear molecule, non-linear as in something which is not arranged along a line. Okay, for a line there is something similar which is called Pyrrhus distortion, but here we are interested in molecules which are not, where atoms are not arranged in a line. So in that sense, nonlinear molecule. If a nonlinear molecule has an electronically degenerate ground state, okay, so that means you have a ground state which is degenerate. That is an amazing thing. Okay, then Yarn-Teller theorem says that immediately, see, the degeneracy is always related to symmetry, and IH is a very high level of symmetry. So Yarn-Teller theorem says that if you have a degenerate ground state, that structure will immediately undergo distortion and go to a lower symmetry structure such that the degeneracy is lifted. Okay, so that is nuclei will move to a lower symmetry structure because it's the location of the nuclei which decides the structure and point group. And and also, see, it's not just lowering the symmetry, it should also lower the energy. Okay, so it should, the high symmetry degenerate structure should go to a lower symmetry non-degenerate structure which has lower energy, otherwise it will not go. Okay, energy also has to be lower. So here we know that icosahedron has a very high symmetry and that is unstable, while the true ground state has C3b symmetry, which is much lower than IH. Okay, and the energy of C3b symmetry is C3b structure is 3.86 eV. lower than IH structure. So all these conditions are being satisfied, lower symmetry, lower energy. Okay. So then, I mean, does IH structure have a degenerate ground state or not? Okay. So let us see. So what we did is that we calculated the orbitals, okay, or we removed all the electrons, okay, and using the basis functions, Gaussian basis functions, we calculated the orbitals. So by removing all the electrons, we removed all the electron repulsion effects, and now the orbitals will respect truly the symmetry of the arrangement of nuclei in the E12. And then we say that once we have the orbitals, we start applying the Aufbau principle. Okay, and this is a scenario for IH structure. So here Ag, T1U, etc. are irreducible representations of the IH group. And if you start filling the electrons, so you boron has 5 atoms and 5 electrons, and you have I mean, and you have 12 boron atoms. So in all, you have 60 electrons, and you start, but 12 of those will be filling the core orbitals. So I have removed those. Okay, and you start filling these electrons. What you realize is that our HOMO is actually five-fold symmetric. Okay, it has a five-fold degeneracy. Okay, but the total number of electrons, that is 60, if you start applying Aufbau principle, then you see that if you fill any of these two 5 HOMO orbitals, 3 are still unfilled. Okay, so that means you have a lot of degeneracy. You can arrange these 4 electrons in many ways because they are all degenerate orbitals. We can arrange these 4 electrons in many ways. Okay, so there are many possible configurations for the ground state. Okay, so clearly we have a degenerate ground state here. Okay? Because you can put 1 electron here, or arrange 4 electrons as singly occupied, and singly occupy all the 5, and you still have one unfilled HOMO. Okay, so there's a huge amount of degeneracy. So this is a clear-cut case of Jahn-Teller effect. Okay, so you have a degeneracy at the, I mean, in the ground state. Okay, so according to Jahn-Teller theorem, it should distort. So then we perform the similar analysis for the C3V structure. Okay, again the number of atoms is the same, number of electrons is the same. However, the symmetry of the arrangement of atoms is now C3V, and if we apply the Aufbau principle, we see that there is no degeneracy in the ground state. Okay, the orbitals are uniquely filled up to HOMO, and everything above it within the 1 electron theory is empty. Okay, so this looks like a clear-cut case of Jahn-Teller distortion. Okay, that icosahedral structure had huge ground state degeneracy, and clearly it was untenable as far as Jahn-Teller theorem is concerned. Okay, and C3V structure, which is the true ground state, has, I mean, no such degeneracy. I mean, it has all the filled HOMOs and then all vacant unoccupied orbitals. So it is quite indicative. Situation is quite suggestive of Jahn-Teller distortion. But why am I saying that it is suggestive and not an absolute confirmation? Okay, the reason. Okay, so I'll come to that. So according to 1 electron theory, high symmetry IH structure has a degenerate ground state, as we saw. Low symmetry C3V structure has non-degenerate ground state. Okay, and according to, because we perform the geometry optimization using coupled cluster singles and doubles, and so according to our coupled cluster singles and doubles calculation, the lower symmetry structure has 3.86 eV lower energy. So all the conditions for Jahn-Teller distortion are being satisfied. Okay. However, what is missing is that if we could find the reaction pathway, okay, how does it distort? Does it distort directly from a shell? I mean, if we have the initial structure to be a icosahedron, which is a cage, while the final structure C3 is an open structure, how does it happen? What is the reaction pathway? Okay, reaction coordinates or reaction pathway. Does it happen directly or does it happen in steps? Okay, So these are challenges for the future. But as far as the basics of Yarn-Taylor distortion is or Yarn-Taylor effect are concerned, it seems to satisfy. But it will be very nice if one could do the calculation and find. Suppose we have a boron 12 icosahedron. In what steps, through what intermediate states it will distort so as to end up with that C3B type of structure. Okay, but I encourage any one of you to take up this problem and settle the issue once and for all. Okay, then later on, what we did is that we thought that if B12 has such so many isomers, then can we get an optical fingerprint, just like we got the optical fingerprint of the spin state, spin multiplicity for octacene, nonacene, etc. Can we get an optical fingerprint of the structures? Of course, the structures can be also identified using vibrational spectroscopy, but many people don't want to do vibrational spectroscopy, and they may want to see if they can also be different structures can also be identified in the optical absorption spectrum. Okay, so with that aim, we calculated the optical absorption spectra of lowest three isomers. Okay, and then we just look at the spectrum and see and try to analyze as to whether it leaves a structural fingerprint. That is, for three structures, three different types of optical absorption spectra are obtained or not. Okay, so for that we did multi-reference singles and double CI calculations. Okay, for quasi-planar structure, C3V is a non-abelian group, so naturally we will use some subgroup of it or a D2H and its subgroups. So we used CS point group, okay, and here for chain structure we use C2H because that is a abelian subgroup of D2U and D2H. Okay, here is the size of the calculations. You can see that for quasi-planar 6.9 million, okay, 5.2 million, 6.74 million configurations, and here for chain we are almost approaching 10 million. So these calculations were truly large scale. So results will be reliable. We have to do these large scale calculations for the reasons I mentioned earlier, that for optical absorption calculations, we not only need the ground state, but we also need the excited states. So that's why the Hilbert space size becomes huge. Now, here are the calculated optical absorption spectra for various parameters, but here we have to compare them to each other. See, quasi-planar structure has a peak, intense peak, around 5 between 5.75. Double ring structure, and other than that, there are weaker peaks. Double ring structure has an intense peak below 5, and then an intense peak above 6.5. Okay, and chain structure has an intense peak around 4.5 eV. Okay, and intensity profiles are also quite different. So if we have a mixed ensemble of these clusters, B12 clusters, and we don't know which ones are which, then using optical absorption spectroscopy, we should be certainly able to distinguish one from the other. Okay, so why is this important? So this is called structure property relationship. The geometry determines various properties, and in this particular case, the property happens to be the optical absorption spectrum. Okay, so so clusters, the reason this is important is clusters produced in a lab are generally mixtures of various molecular weights and isomers. Okay, so mass spectrometry can only determine the molecular weight, but not the structure. So because of this, I mean, clear-cut optical fingerprints vis-a-vis the structure, okay, we can say that the photoabsorption spectra should allow us to distinguish between three isomers of B12. Okay, so thus we see a strong structure property relationship here as far as optical absorption, and therefore we suggest that optical absorption spectroscopy can be used for identifying the isomers, structures of the isomers. Okay, so I wanted to really cover this because this was somewhat different as compared to other topics. Now it is 2:46. So how much time do I have? I have I suppose I have 1 hour, so I can go to one of the graphene quantum dot problems, okay, and then come back. So it's a linear, non-linear type of hop. So I reach the end of my presentation and then I'm coming back. Okay, so let me, because I have some time remaining, I can utilize that. Or if people are getting bored, then we can have a discussion right away. It's up to you. Or otherwise, I can discuss this graphene quantum dots with stone waves defects. Okay,
So
so
you
let
have
me.
25 minutes more.
Hello. Yeah,
You have 25 minutes more.
I have 25 more minutes.
Yes, sir.
Okay, but uh, in the morning session, we had 1 hour of discussion. I mean, 1 hour of talk, followed by 15 minutes of discussion. So anyway, let me continue. Let us see how much I am able to continue by. I mean, how much I am able to cover by 3 o'clock, and after that we'll take a call. So at 3 o'clock the discussion will start, right? I mean, if people have questions. Okay. So let's uh, discuss this. This was a very nice idea of these two collaborators of mine. Both have the name initials TD, Tisa, but they are sisters, both physicists. Okay, and one is Tista, who was my postdoc, and other one is Tushima, and both are employed in Bombay in different colleges. Okay, and both Tushima had done her PhD in experimental high energy physics, but she also changed because it's not easy to do experimental high energy physics in India. So she changed to this field. While Tushima was my postdoc, so she was already trained. Okay, so the idea was very nice. Okay, so motivation for this study is that pristine graphene quantum dots cannot be used for efficient visible light harvesting devices. Okay, their absorption spectrum normally doesn't falls outside the visible range. Okay, and the reason is, like I said, they are poor absorbers of light in the visible range. So the question they thought about is that can we make some structural changes in graphene quantum dots, okay, and so that they begin to absorb more in the visible range. And we define the visible range to be from red to violet, which is roughly 1.5 ev to 3 ev. Okay, so and to explore, so then it occurred to us, why don't we, because in graphene it's well known that in graphene structures a very common structural defect is stone Wales defect, which is azulinic structure, heptagon or septagon and pentagon fused together. I'll show that. Okay. If we introduce, so they just got this nice idea and started pursuing it. That what if we introduce a stone Wales defect? Okay. They didn't anticipate that it will lead to more light absorption in the visible range. They just wanted to investigate, okay, as to what happens to the optical absorption spectrum when they have a stone Wales defect in the graphene quantum. But stone Wales defect, for stone Wales defect, you have to have a reasonably large sized quantum dot. Okay. So what they did is they considered a 64 atom rectangular type of structure shown here on the left. Okay. Then they obtained two structures with stone Wales defect. One has stone Wales in the middle. So the middle one has the stone Wales defect in at the edge, and you can see the stone Wales defect is here. Here, this ring is a seven-membered ring, septagon, okay, and then you have a pentagon fused to it. So that is a stone Wales defect, single stone Wales defect, okay, okay, uh, and then oh well, actually it's not single, it's double, okay. So one stone Wales here and another one here, okay, and the other one is, you can see that there's a stone Wales effect here, okay, here. Okay, so the question is, First of all, I mean, it's easy to visualize, it's easy to imagine, but the thing is that do they really exist? So here we had to go beyond. The first step was to do first principles calculations, okay, to really find out whether stone Wales defect can be stabilized in these systems or not. Okay, so they did the calculations here. Okay, so obviously the defect-free system has the which they call GQD 64. Then the second structure they call SW1, Stone Wales 1, and the other one is Stone Wales 2. Okay, so clearly GQD structure, that is the defect-free structure, should have the lowest energy. Then using their first principles calculations at the Hartree Fock level, relative uh, restricted Hartree Fock level, okay, they found SW1 to be 2.77 eV higher in energy, ground state energy, and SW to be 4.14. So naturally, because they are higher in energy, so naturally the system in its, I mean, if the system is left to its own devices, it will only exist in the lowest energy state, that is the GQB 64. So one has to find, in order for these to be possible, one has to have the technology of stabilizing the stone Wales defect. Okay, so that is something for nanotechnologists to do. But in our case, we assume that if these defects do exist, then what happens to the optical absorption spectrum? Okay, GQDs with the reconstructed edges, zigzag edges, are more stable compared to GQDs with the SW defect in the middle. Okay, so this is more stable as compared to this. And clearly, the stability of GQDs depends crucially on the location of the defects. Okay, then we calculated the I mean the homo-lumo band gap. Okay, and at tight binding level we got 1.13 for the symmetric system and 1.13 for the symmetric system. And at the correlated MRSDCI level, the gap increases, which is not too surprising because tight binding model underestimates the gap. Okay, so that is a trend everywhere. Okay, now the main thing here, because there are many technical details, and the approach is the same. That is, we have used MRSD-CI approach to calculate the optical absorption spectrum of the pristine system as well as optical absorption spectrum of the defective systems, both at tight binding model level. So tight binding model, you can see that the energy gaps are really tiny, and at the PPP model level at MRS using high quality MRSD-CI calculations. Okay, and so basically all the results are contained here. So you can see that there is a spectral weight shifting in such a manner, and we not only looked at the absorption spectrum, we also analyzed the oscillator strengths corresponding to the absorption, and based upon that we made the, and by the way, these calculations were very large scale, and stone Wales systems don't have any point group symmetry, so the Hamiltonian matrix, CI matrix, was very huge. Okay, and it took many days to do these calculations and to analyze the results. Okay, so there are lots of things here. We have given the nature of optical excitations, that is, which peak corresponds to what kind of states, but that is not the important point. The important point is that for the pristine, 59% of the total absorption spectrum is in the visible domain. Okay, but when we have stone Wales defects, SW1, then 65% goes in the visible domain, and when we have SW2, 83% of the optical absorption spectrum is in the visible domain. So our conclusion was that we have, I mean, the stabilization of stone Wales defects, uh, I mean, concentrates the absorption spectrum in the visible range, which is like, which I mentioned earlier, that is 1.5 to significant portion of absorption spectrum, that is up to 83%. In the visible domain, that is 1.5 eV to 3 eV. Okay, And so this is something desirable. Now the question is for experimentalists and technologists whether it is possible to stabilize these defects. Okay. So this is the basic essence of this work. Rest are all technical details. If anyone is interested in knowing what these graphs mean, okay, then we can discuss it. But this is the essence of the work. Okay, and this is another work with Preetham, our last speaker today, that we were inspired by the work which we did with Sumit on coronine. So if you were to remove these benzene rings, you have the hexagonal structure which I had shown earlier, which also has the same symmetry as benzene, that is D6H. Okay, so we just wanted to have a look at as to what happens when we lower the symmetry. So here we have added one benzene ring to coronine, so it is called benzo A coronine. Here we have added naphthalene to coronine, so it is called naphtho 23A coronine. Then we have added three benzene rings, that is anthracene. Okay, so it is called anthracoronine. And here we have added a naphthalene in a different manner, that is we have fused it here on these two sides. So this is called naphtha 812 coronine. And again, the same methodology has been applied. Okay, and for example, let me see. Okay, so the essence of the work here is that these structures, the symmetries are different. Okay, for example, coronine, like I mentioned, is D6H. When we add one benzo, we go to benzocoronine, then the symmetry reduces to C2B. Okay, and when we have naphthocoronine of the on the sides, okay, not elongated one, okay, on the sides, then the symmetry is CS. Okay, so the question is, if we change the symmetry, how does the absorption spectrum change? And you can see again, you have a very nice structure property type of relationship. Okay, so this is from our original paper with Sumit from 2014. We have one strong peak and several smaller peaks, but for benzocoronine we have two strong peaks, okay, which are well separated. And for naphtho 812 coronine we have two large peaks and several smaller peaks, but of significant intensity. Okay, so again, there is a structure property relationship. And how do we? Someone had asked that how do we validate our results? So we found results, experimental results only for of these. We found for benzo A coronine, okay, they gave one absorption peak at 3.38 eV. So our MRSD calculations are in very good agreement with that, within 0.04 eV for the screen parameters. Okay, and for naphtho 812 coronine, okay, also one absorption peak was available. Okay, these for other ones there is no, we couldn't find any experimental data. So they are also standard parameter results are 3.23, screen parameter 2.95, and the experimental work is 3.42. So it's quite close to the screen parameter results. So this is how we validate our calculations. Wherever we can find experimental data, so we compare it with that, and if our calculations agree, then it's a good thing. Otherwise, I mean, something is wrong, either with our calculations or with the experimental data. Okay, so this is 3 o'clock now. So I mean, I can take questions now. I have spoken for 1 hour, or otherwise, yes.
Hello, Shumik here. Can you hear me? So we had
Too bad I couldn't come. Otherwise, I would have met you.
I was looking forward to meeting you.
Are you coming to Bombay?
No, only Pune, but this is not the place to discuss that.
Okay.
We'll be in touch. Okay, so I had you had something very interesting on the boron clusters. you found that the icosahedral is lower energy within one electron theory, and the C3b is lower electron within the correlated, lower energy within the correlated electron theory. And then you explain that by bringing in Jahn-Teller distortion, which I understand because Jahn-Teller distortion is a one electron explanation. Why would that explain why C3b is lower?
No, actually, within one electron theory, we didn't calculate the total energy. We were just looking at the degeneracy of the ground state. Here, we didn't
Right.
see, we calculated the total energy only within the correlated electron theory. Okay, so within the correlated electron theory, these are all CCSD results. CCSD actually T, even triplet excitation included perturbatively. So lowest energy structure is C3b, and perfect icosahedral structure is 3.86 eV higher than that. Okay, so and it satisfies Jahn-Teller in the sense that, so we wanted to see whether it has, for it to be a Jahn-Teller system, that structure should have a degenerate ground state. Okay, so so we calculated, and because Jahn-Teller distortion is basically a one electron theory. Okay, so we calculated the orbitals, molecular orbitals. Okay, and this is what we get. So we have 5 degenerate homos, but only 2 of those can be doubly occupied, or 4 of those can be singly occupied. Okay, and within one electron theory, they are all degenerate configurations. So according to Jahn-Teller theorem, this such a state cannot exist. Okay, so that means it should distort to a lower energy structure. But the question is, what is missing from our description? So it is all very suggestive. It is distorting. The ground state is truly a lower energy structure, C3b, significantly lower energy than this. IH has ground state degeneracy, but what is missing is the reaction pathway, the mechanism. How, if I create a cluster with IH symmetry, that is perfect icosahedron, in what way does it distort to C3b? How does it reach? Because there may be other structures which are stable, which are local, which correspond to local minima, not global minima. Global minimum is confirmed to be C3b. So does it proceed through those local minima? For example, we found two other higher energy structures as compared to C3b, which are perfectly stable. Okay, so like D6b and C2H, they are also stable, but they are higher in energy. So my question is, or our curiosity was, that here we definitely have within one electron theory a degenerate ground state. Okay, if we go from IH to C3b, how do we proceed? When we just did calculations, our calculation suggests that it goes to from icosahedron to distorted icosahedron, but that is also unstable state. So we didn't actually pursue it. I should have pursued that. If I take D2H, then where does it go? Does it go to the next lower energy? So my question is, or our curiosity is, whether it's a direct distortion, quick direct distortion from IH to C3b, that is the cage suddenly bursts and opens up, or if it is a stepwise distortion. That for that one has to do more like involved calculations. See, here are these three are stable structures. So from here, how do we reach here? That is the question.
Okay, thank you.
Yeah.
Any other questions from the audience? Yeah, yes, please.
Hello, sir.
Hello.
Yeah, sir. This optimized geometry, are you? I mean, is based on error and. I mean, how do you are? How you are? Hello, can you hear me, sir?
Hmm?
Can you hear me?
Yeah, I can hear you.
Yeah, sir. How you? I mean, how you are getting this optimized geometry?
How we are getting these optimized geometries?
Yeah.
Actually, what we have done See, most of the structures you will have to give some initial structure. Okay, for most of the geometry optimizers, you have to give some initial structure, and then they will uh, go to the lowest, either lowest local minimum or the nearest local minimum as compared to that structure, or nearest saddle point also. Okay, so for example, when we gave IH type of structure, that is all the bond lengths being the same and arranged in this perfect icosahedral way, it did not distort in the beginning. It just changed the geometry. I mean, it changed the A value bond lengths, but it ended up here. But then when we did, so we have to confirm whether we are at a saddle point or whether we are at a global minimum, okay, global or local minimum. So we did the vibrational frequency analysis, okay, and then we found those imaginary frequencies. So you have to somehow, that creativity about what kind of structure does boron form. Okay, so that contribution, that was a very important contribution which Ehsan Bustani brought into the thing. He has been studying, I mean, if you look at his papers from 80s, filled with, he has n number of publications in PRB, JCP, and all that, and he has that wisdom as to what kind of structures are possible. So that was his very important contribution, and we supplied the computational aspects and did the optical absorption calculations and all those things. So he has some intuition, okay, what structures are there. So we worked according to his intuition. Some turned out to be stable, others turned out to be, like unstable. Okay, so that's how people do it. I mean, you have to have some idea about, either from intuition or from prior calculations, what type of structures does boron make.
Okay, sir. Thank you, sir.
Any other questions? Any questions from the online participants?
Yeah, I see one question here, one comment.
From Shukla Shatra.
As the reaction pathways are decided from the selection rule, isn't it? As far as nuclear vibrations are concerned, yes, there will be selection rules and all those things. So, but this is a field where we don't have much experience. Okay, I truly want to understand how does IH reach C3V? How does IH become C3V? Okay, and so reaction pathway, as has been correctly pointed out. I mean, there are various constraints involved. Okay, but it can be done, but it's not an easy task. So that is why we sort of gave up, because we had already done a lot of work. So if there is someone here who wants to pursue this, this is an open problem. People have done yarn teller distortion of I structure using model Hamiltonians, but no one, to the best of my knowledge, has done it using first principles methodology.
Okay, so any other questions? Yeah, I actually have one question. So I think you skipped the theorem about ferrimagnetism, right?
I'm sorry, I was not able to understand.
You skipped the theorem about ferrimagnetism. Can you hear me?
Actually, the voice is not very clear. If someone in SN Bose understands this, then please convey it to me.
Sir, can you hear me?
Yeah, I can hear you.
Okay, can you hear me? No?
Yeah. Yes.
So my question is, I think you skipped the theorem about ferrimagnetism, right?
Huh?
Ferrimagnetism.
Ferrimagnetic?
Leap, Lieb, L-I-E-B.
Heights theorem or N-I-E-B, Leap.
Lieb.
Elliot Leap.
Uh,
Okay, yeah.
okay.
Maybe.
I'm able to understand ferrimagnetic, but in what context I can't.
I think at some point you showed you wrote something about Leib's theorem.
Okay.
That one.
Leib's theorem. Okay. I didn't get to that particular problem, but I can leave because I ran out of time. Okay,
Okay.
but I can discuss. I can tell you the basics of it. This was in the context of triangular quantum rods. Yeah, this one. Yeah. So
What did you want to
Leib's
please
theorem
go ahead.
yeah. So Leib's theorem says that if you have a bipartite system with A type of atoms and B type of sites, okay, A type and B type, then the ground state spin multiplicity will be equal to half of, or ground state spin will be half of the difference of A and B type of sites. So if we consider this triangular dot with structure with the, let's say, 6 benzene rings, then it has n equal to 22, and it applies to even sited systems, even number of sites. So n equal to 22 is even number of sites, but if you look at assign anyone randomly A, then all its nearest neighbors will be B, and their nearest neighbors will be A. Then if you count, then A type will turn out to be 12. There are 12 A type of sites and 10 B type of sites. Okay, so then the spin multiplicity of this structure will be S equal to 1. That means the high spin states, because it's an even electron system with 22 electrons, pi electrons. So the high spin state, I mean, the most logical thing should be that it should have a singlet ground state. But according to Leib's theorem, it should have a triplet ground state. Okay, so what we did is that we did high-powered MRSG-CI calculation. Okay, so this is the, and indeed, but by the way, Leib's theorem is based upon nearest neighbor tight binding plus Hubbard model. But in our case, we are using PPP model. So we just wanted to explore whether in PPP model, what result do we get? I mean, what is the influence of long range Coulomb interactions? Okay, and what we found is that, so here it is given. Okay, or let me go to the slideshow mode. Okay, so we found using both sets of parameters that for singlet, the total energy was minus 49.84 eV, but for triplet it was minus 51.86 eV. So that means indeed the triplet state, high spin state, is the ground state here, unlike in case of earlier scenes. Okay, and using screen parameters also we got a triplet to be lower energy. So that means irrespective of the parameters and even with the long range Coulomb interactions, we are getting triplet to be lower energy as compared to singlet. Okay, so which is quite remarkable, and it confirms Leib's theorem, but or it confirms the Leib's result which he obtained using the Hubbard model also for the PPP model. So this was, yeah, this is something, this is also very interesting. And
Okay, yes. Thanks
so
for
I
this.
managed to discuss that. Okay.
Any other questions? If not, let's thank Professor Alok Shukla again.
Okay, thank you. Thanks a lot.
Thank you very much.
Yeah.
So we have 30 minutes.